Hello everybody, today we will be talking about the properties of integral. I think this is like section 5.2 still, so I kind of lost track of it already, so bear with me hopefully. Okay, today, as we said, we're looking at the following. How to solve for the definite integral geometrically. And keep in mind that definite integral is just another fancy way of saying the area under the curve. So we'll be looking at that, and also how to solve for the definite integral using the properties of the integral. So we'll talk about those properties in a little bit, and then afterwards how to actually approach them. All right, so here we go. So here is the first problem, jumping straight into it because there's nothing really to be learned in this case. That's new anyways. I want to solve for the integral from -3 to 3 of square root of 9 minus x squared. Now, if you saw the last video, something like this, you should be able to be familiar as to like what is it really asking for. This right here is really just a semicircle with a radius of 3 that is centered at 0, 0 because of the equation. If you want, you can say that this is equal to y. So then that way you would have y squared is equal to 9 minus x squared, and y squared plus x squared is equal to 9. So you can see how that is supposed to be a circle, but because y is equal to the square root of 9 minus x squared, rather than y squared plus x squared is equal to 9, then that means it's only the upper half of the circle because y has to be positive. So the picture of the graph looks something like the following, and what I need you to do for this problem is solve for the area under the curve from here to here, because it says specifically from -3 to 3. Well, there's no fancy trick to this. It's just the area under the curve then. So that means it's the area of this half circle. So the final answer for this one is going to be pi r squared and then multiplied by 1/2. So 4.5 pi, that is going to be the answer then. Okay, so some of these, yes, you might as if you don't know how to solve for the integral, the best way is to look at it geometrically then, especially if it's an equation that's like looking really funky. Okay, here's another example. Let's say this time it's the area under the curve from -2 to 3 of the absolute value of x plus 1. So once again, we're going to go ahead and graph what that looks like so you can see what the area under the curve actually looks like then. Absolute value of x plus 1, so that means it's going to be a V-shaped graph, so it looks something like this. And I want to find out, this is going to be -1. And I want to find out the area from -2 all the way to +3. So then this region over here, as you can see, is what I'm looking for. And you'll note that the result is really just the shape of two triangles. Okay, so all of these pictures, you should be able to find the area because they're geometrical figures that you know how to find the area from in geometry. Okay, so go ahead and finish this off. Let's see. The first part right here, that's going to be a triangle. It looks like their base is going to be a length of 1. So let me just kind of use a different pencil for this one. So this is going to be a length of 1. And you can see over here, this looks like it's going to be a length of 1 also. And if you want to verify, just go ahead and plug in x equals to -2 into the equation, and you'll see that result as well. Then for the other part, it's going to be a base of 3. And the height in this case is going to be 2 because, again, you're just plugging into the equation then. Let's see. So my final answer is going to be the area of this square, the half a square, so that's 0.5. And then the area of, actually I kind of messed up because the base is not 3, but rather it's 4 because it's from -1 to 3 then. So let me go ahead and change that before I kind of make that mistake. So 1/2 base times height, that's the area of a triangle once again. So 4 times 2 times 1/2, so that is going to be 4. So my answer in this case is going to be 4.5. Okay. All right, next, let's look at this last example geometrically then. Okay, this time I am going to go from the area from 0 to 6, and I want to go from, for the equation, 3x minus 6. Okay, so let's go ahead and draw that out once again. Okay, and by the way, not every single area under the curve can be solved like this geometrically. It's just some of them where you can recognize what the shape is going to be. So later on, we're going to be talking about, well, not in this session, but maybe in the near future, we'll talk about how to actually solve for the actual area under the curve if you have, like, say, a nasty looking equation. All right, but anyhow, going back to this, this is going to be a linear equation where the y-intercept is going to be at -6. Okay, so here is the -6. The x-intercept is supposed to be 2, right? Because if you plug in 2, you're going to get 0 for y. And I want to go all the way from 0 all the way to 6. So that means it's going to be something like this. And once again, you can see that we actually have two triangles that we're trying to find the area for. Now, be very careful in this case because there is a difference between the triangle above whereas the triangle below. The triangle that's below the x-axis, because it's negative, then we consider its area to be negative. So what that means is technically sometimes your integral, your answer, could be equal to 0 because the top area and the bottom area, they might net each other. So watch out for that. But anyhow, let's go ahead and dive into it. Let's see. For the first triangle over here, the length is going to be 2. The bottom part, that's going to be 6. So then that means that this area is going to be 2 times 6 times 1/2, which is equal to -6 then. Because again, remember we said the area underneath the x-axis should be negative. But whereas the top part, the base over here is going to be 4. And then the height over here, well, I think we're going to have to plug in this 6 into the equation. So let's go ahead and do that. That is going to be, let's see, 3 times 6 minus 6. So that is equal to 12. So that is going to be our height right there. So 12. Okay. Once again, the area under the curve. Let's see, that is going to be 4 times 12 multiplied by 1/2. So that is equal to 24 then. So final answer is going to be 24 minus 6, which is equal to 18. All right. So, when you do these problems, again, don't be freaked out if your area could potentially be equal to 0 because the area above the curve could be the same as the area underneath the curve. Just to give you like a side example, maybe what we can do is look at the cosine equation, right? Look at the cosine from, let's say, the integral from 0 to pi of cosine of x. Now, when you draw this, you can see that geometrically, okay, cosine looks like the following. It starts at 1, and then it goes to 0 when it hits pi, and then afterwards, pi over 2, that's when it hits 0, and then afterward, when you get to pi, you get to -1. So note that how the graph of cosine is geometrically the same as it is symmetric above as it is below the x-axis. So that means that this area is very likely to be same as this area right here because the shape is going to be the same. So that means that this is actually equal to 0 then. Okay. All right, so let's go on, and now let's look ahead and talk about the properties of the integral. These properties are very, basic for the most part because they're kind of like the limit property. If you take a look at them and you analyze them geometrically, you say, oh yeah, that's the reason why that's actually going to work then, okay? So let's kind of, talk about each one quickly. The first one was actually a derivation that we did from last time where we said that if you want to solve for the area under the curve via the limits, you can write it in this form over here that's on the right. So limit as n approaches towards infinity, where n is the number of partitions. The first part of it is b minus a because that is supposed to be the base of the curve that you're trying to find the area under the curve for, divided by n because you're breaking it into n number of partitions. Whereas this guy right here is going to be the sum of all of the heights. So this is the height part, and then this is the base part, and you're going to take the summation of it. Well, that's where this part comes in, but technically it could be in front of the base or behind the base. Doesn't matter. Okay. The first property that we can talk about, I guess, the first official property in this case, is that here, if you have the area from b to a of f of x dx, that is the same thing as the area from a to b of f of x dx by putting a negative in front. The way we can derive that is we can actually take this expression, number 1 over here, and literally just plug in, as you can see. And you'll notice what's going to happen is the base is going to change. In one case on the left, it's going to be a minus b over n. And then the case on the right is going to be b minus a over n. And because there is a negative on the right-hand side, then you can see that those two are going to be the same thing, then equivalent to each other. So you can actually swap the integral so that the lower bound becomes the upper bound and vice versa by just introducing a negative in front. Okay, second one right here, the area under the curve with from a to a is f of x is equal to 0. Well, hopefully that you can understand why, because if you're going from a to a, then that means there's no base, so hence there's no area then. The next one, a little bit more tricky, the area from A to B of the constant C. So here, if I drew it geometrically for you, just to show you what that looks like, this is like saying the following then. Y is equal to C, that's a constant, right? So that means it's a horizontal line. So here is Y is equal to C. Here is some point A, here's some point B. I want to find what is the area underneath the curve that is going to be that situation. And if you notice geometrically, what we have here is really just a rectangle. So the area of that rectangle is going to be base times height, the base being B minus A once again, and then the height is going to be C because that is the Y value that corresponds over here then, okay? All right, next part, number 5. This says that if you have the integral from A to C of f of x, you can split that up into 2 parts. Area from A to B of f of x plus area of B to C of f of x, so long as B is in between A and B, A and C. Okay, so assuming that the entire time all of these functions are continuous, though. Okay, they have to be continuous for us to be able to do this. Okay, so next one right here. If f of x is greater than 0, then for if f of x is greater than 0 for all of x between a and b, then the area under the curve of f of x from a to b is going to be greater than 0. Well, we just kind of showed that over here. So you can see that if your curve is strictly above the x-axis, then that means the area under the curve should be positive in this case. And that's what number 6 is talking about. Next one, number 7. This is kind of like, in a way, almost like a half of a squeeze theorem. It says that if you have a function where one is greater than the other within an interval from a to b, then the area under the curve of the upper function is going to be greater than the area under the curve for the smaller function. So hopefully that part makes sense to you. Again, just let me draw it out visually so you can see. So f of x is somewhere over here. G of x is somewhere down here, and it's always a case where f is greater than g within that interval from a to b. Then the conclusion is that the area under the curve for g is going to be smaller than the area under the curve for f. So that's number 7. And finally, for this one, number 8 over here, this one's not as easy to see though. It says that if f of x has a lower bound, which is the lowercase m, and an upper bound, which is an uppercase m, for x that's between a to b, then m times b minus a is going to be less than or equal to the area under the curve is less than or equal to capital M times B minus A. So this is kind of a play off of number 4 that we said over here, because as you can see, you have some sort of constant multiplied by B minus A. So that means we have some sort of rectangle to kind of go by. So here, let me just kind of draw what this is actually saying then. Let's say that you have the curve, right? Let's say go ahead and you have f of x, okay? So something like this right here. And let's go ahead and say that this part is b, and this part over here is going to be a. They're saying that a curve has a lower bound, which is going to be m. So that's going to be my absolute minimum. Whereas the top part, that is going to be my absolute maximum. So you can see, hopefully, that the area under the curve is going to be this portion that's over here. Okay, so that's what we want to focus on. Now let's think about the other part. Lowercase m times b minus a, that is supposed to be the rectangle that is going to be formed by the lowercase m multiplied by the base. So this right here, that is going to be m multiplied by b minus a. But whereas for the upper part right here, let's see if I can, draw it with a different color. Okay, let's use black in this case. You can see m is over here. If I draw a horizontal line, and then we draw the base part over here, then that is that black part, the black rectangle, that has an area of capital M minus b times b minus a. Okay. All right, so, all that talk, it's kind of worthless if we're not going to apply it. So let's go ahead and look at a few examples of this then, okay? So what I want to do now is I'm going to be given the following properties over here, okay? So I'm going to be given the following integral facts. One is that you have f of x, if you're looking for the area under the curve between -2 to 6 is equal to 10. The area under the curve for f from 2 to 5 is going to be -4, so that means it's probably below the x-axis. And finally, you have another equation, g of x, from -2 to 6 is equal to 3. And I want you to find the following over here. Okay, so let's go ahead and use the properties to see if we can actually solve for each one of these. First, what we can do is we can break these up into two parts. If you remember, just like the limit laws, we can go ahead and do the same for the integrals. So that is to say, I'm going to go ahead and split this up. So it's from -2 to 6 of 3 times f of x, and then dx, minus the integral from -2 to 6 of 2 times g of x dx. So just kind of like look at them independently. I'll go ahead and take out the 3 because, you know, if you're multiplying 3 to a function, it is the same as taking it outside. Just exactly, again, the same thing as the limit laws. So 3 multiplied by -2 to 6 of f of x dx minus 2 multiplied by the integral from -2 to 6 of g of x dx. And all of these guys right here, you should be able to solve for because the first part right here, well, we're given that's equal to 10. So 3 times 10 minus 2 multiplied by this guy over here, we are given as 3. So my final answer looks like it's going to be 30 minus 6, which is equal to 24. Okay. Okay, let's look at the second one right here. Same idea. The area under the curve from 5 to 6 is a little bit different because we don't have a 5 for a lower bound of f of x, and also for g of x squared from 3 to 3. Well, as nasty as it looks, it actually is not that bad because you basically kind of have to do a combination here in order to see what's actually happening. Now, as I said, I don't have from 5 to 6 that's given to us for f of x. But what we do have is the following. If you notice that, let me just kind of write this on the side over here, the integral from -2 to 6 of f of x dx, that, according to the property, is the same thing as -2 to 5 of f of x dx. And then, let's see, and you're going to take that and add it with 5 to 6 of f of x dx. Okay, so we can actually split that into two parts. And I think I realized I made a mistake. Well, let's see. Maybe I did. Oh, yes, I did. Let me go ahead and cheat right now and say that this guy right here, for the middle one, is going to be equal to -2. Okay, so sorry about that. Didn't think about that ahead of time, so that was my fault. But anyhow, that's the idea if we find the first one. I'm going to split it into two separate integrals, so that way you can see how that works out. Well, since we know this is true according to the property, then that means what I'm trying to solve for, which is this guy, is going to be the upper minus the lower. So this is going to be the following then. -2 to 6 of f of x dx minus the integral from -2 to 5 of f of x dx. Okay. And then we have minus the integral from 3 to 3 of g of x quantity squared dx. Okay, so we can take that split integral and split it, and then subtract from 1 and then get what we actually want. So now again, it's just a matter of plugging things in. So we'll go ahead and do that now. The first part is supposed to be equal to 10 because of the first piece. Then the second part is supposed to be equal to -4, so 10 minus -4, okay? And then minus, now for the last part, be very careful. The answer is not equal to 9 because, you know, you see g squared and the first thing that comes to mind is, oh, g is equal to 3, so therefore, then the whole thing is going to be equal to 9 then. That's not how it works, unfortunately. But here is what I did notice. You are going from 3 to 3, so that means that no matter what the function is, the base size is still always going to be equal to 0, so that means 0 is going to be its answer. So that now is going to give us a final answer of 14 then. Okay. All right. Let's look at the last example over here. Let's say this time the area under the curve from 6 to -2 of f of x minus 10 dx. So what I don't like about this problem is that the lower bound is greater than the upper bound. So if you remember the property over here at the very top, number 2 in this case, where it says that we can go ahead and swap the lower bound and the upper bound by just throwing a negative in front of it. So that's what I'm going to do. Okay, so I'm going to take this problem and I'm going to make it so that it's negative from -2 to 6 of f of x dx, and then minus 10. So that is going to be my first thing. Now I'm going to go ahead and separate them. So it's going to be negative integral from -2 to 6 of f of x dx. And then it's going to be plus the area under the curve from -2 to 6 of 10 dx. So I just distributed the negative to each part and then split the integral. So then that way we can look them a lot easier. -2 to 6, we have that already. That's supposed to be equal to 10. So I'm going to go ahead and put that in there. -10 plus the other part. Now remember, this 10 right here, that is the horizontal line. So it's like saying, what is the area under the curve from -2 to 6 where the function is supposed to be 10? So for this rectangle that we have is supposed to be 1/2, not 1/2 base times height, but it's just base times height. So that's where that m multiplied by b minus c thing comes in. So it's going to be 8, which is the length from